Every year, thousands of people die because they lose a vital organ, and thousands more suffer, living a compromised life in intensive care units of hospitals, while they wait for someone to donate an organ to them. In Australia right now, there are approximately 2,000 people on donor waiting lists. 50 of these people are children, and they may have to wait up to 4 years for a replacement to find them, hoping that when it does arrive, that it isn't rejected by their bodies. But what if there was another option for these people? What if organs could be manufactured, grown in a laboratory, and tailored to suit each individual person's needs? What if they could be grown in a week? The idea I'm alluding to here is that of tissue engineering. That's where cells are taken from a patient and grown into new tissue and organs in a laboratory, much faster than can be grown in their own bodies. And because the cells originate from the patient, the organ won't be rejected later on. It's a great idea, isn't it? In fact, it's more than a good idea. It's a medical revolution that's already taking place. It's already been demonstrated that thin tissues, such as skin, can be grown in a laboratory. All that's really stopping us from growing whole organs is something called the thick tissue problem. And that is that cells in the center of thick tissue starve and die. So we can't grow thick tissue and whole organs just yet. But what I'm doing is I'm designing a material with a built-in supply network for nutrients made of capillary blood vessels. It's not a trivial task though. The material also has to be strong enough to hold everything in place while it's growing into a new organ. It has to have room for cells to grow into it. It needs to be made of something that the body won't reject, and it must eventually break down and dissolve back into the body after it's been implanted. Believe it or not though, you've already heard of the material that I intend to use. In fact, you've all probably eaten it at some point in your lives. I'm talking about gelatin. That's right, the stuff in aeroplane jelly. You see, gelatin comes from a substance called collagen, which is what most of the tissue in the human body is made of, so it's inherently something that won't be rejected by the body. The only problem with gelatin is, however, is that it tends to dissolve and break down too quickly before we've had a chance to grow organs in it. But I've found a way to make it last just long enough to work by combining it with a natural fruit extract called genopin. Genopin, in a sense, ties together all the loose strings of gelatin so that it holds together long enough to work. I'm also working on a way to shape the gelatin the way I want it. What I'm essentially doing is freezing it and removing the ice crystals from it, leaving behind lots of little holes and pockets for cells to live in. I'm also making tiny channels and tunnels in the gelatin so the blood vessels can grow through it, so that ultimately I can put it all together into a bioreactor that I'll design and use the blood vessels to deliver nutrients to the cells while it grows into a new organ. An organ which can be implanted into a patient in need, where it won't be rejected, all within a week.
Clearly, thank you for that. That's really interesting. Clearly, gelatin doesn't raise antibodies with people. What about your fruit extract? Have you taken that out and exposed? Yeah, because in general, fruits are pretty antigenic, and there's 10% of the population of Australia are atopic and very likely to react to things. So, have you thought about the downstream consequences of adding to your jelly?
I've thought generally about the prospect of adding the genopin to the gel, and it seems that it is quite a safe thing to put in. It's actually FDA and European Union approved as a food additive.
As a food, but not as an organ to go into somebody's body. And the difference, of course, with foods is that the gut protects you.
That's right.
So have you thought about any in vitro work?
Absolutely. I've actually read, there's a study in 1999, there was a group of Chinese scientists that explored the cytotoxicity and the genotoxicity of genopin. And what they found was that genopin was approximately 10,000 times less toxic than glutaraldehyde, which is currently what's used for analogous biomaterials in the same method. It's a cross-linking molecule. Okay, so we're already using glutaraldehyde, and this is 1/10,000th the toxicity of that.
Okay, thank you very much. Answer my question.
Thank you.